Okay, men, welcome back. I hope everyone is doing well and that you got 11.1 down uh, pretty easily. Today we're going to move on to 11.2 and we're going to be talking about inference for two-way tables. The two sample Z procedures of Chapter 10 allow us to compare the proportions of successes and populations for two treatments. What if we want to compare more than two samples or groups? What if we want to compare the distribution of a single categorical variable across several populations or treatments? If we want to do that, we need a new statistical test. The new test starts by presenting the data in a two-way table. Two-way tables have more general uses in comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. So we're going to get into an example. We're going to carry this all the way through. If you look at our two-way table, we are discussing the type of entree that is ordered right here when the type of music is being played. So we've got no music, French music, or Italian music. The first part of this is to calculate the conditional distribution of the entree ordered for each treatment. So we have French. So in no music, French food, we had 30 out of the total 84. We had 11 out of the total 84 that ordered Italian, and other was ordered out of the 84 when none music was playing. When French accordion music was playing, 39 out of 75 people ordered. One person out of 75 ordered Italian, and 35 out of 75 ordered other. When Italian string music was being played, 30 out of the 84, 19 out of 84 ordered Italian, and 35 out of the other category. Part B asked me to make an appropriate graph for comparing the conditional distributions in Part A. So we made right here, we just made some bar graphs for the type of food that was ordered. You got French, Italian, and other for the French music. And then we've got French, Italian, and other for the Italian music. And then here we had the none. So now we need to write a few sentences comparing the distribution of entrees under the three music treatments. So the type of entree that customers buy seems to differ across the three music treatments. Orders of Italian entrees are very low when French music is playing, but are higher when Italian or no music is playing. French entrees seem to be the pretty consistent in the restaurant, as they order more frequently under all music conditions. And then for all three music treatments, the percent of other entrees was similar. So it didn't matter what type of music was playing, the other category for entree is pretty consistent. It's pretty much the same. So here's our problem. How to do many comparisons at once with an overall measure of confidence in all of our conclusions is common in statistics. This is a problem for multiple comparisons. So statistical methods for dealing with multiple comparisons usually have two parts. An overall test to see if there is good evidence of any differences among the parameters that we want to compare, and a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. The overall test uses the familiar chi-squared statistic and distributions. So the two types of test that we will study today is the chi-squared test for homogeneity, and that determines whether the distribution of a categorical variable is the same for each of several populations or treatments. And then we're going to look at the chi-squared test for independence. And this test looks to for convincing evidence that there is an association between the row and column variables. A chi-squared test for homogeneity begins with the following hypotheses. These are important to know. There is no difference in the distribution of a categorical variable for several populations or treatments. and the alternative will be that there is a difference in the distribution of a categorical variable for several populations or treatments. This is different. If we wanted to find the expected counts for a two-way table, this is, you need to know this guy is different right here. So if I wanted to find the expected count for any cell, is the row total times the column total divided by the table total. So that's going to be different for my expected counts. If you skip down here to the bottom, I'm still going to calculate the chi-squared value as observed minus expected quantity squared divided by expected. The conditions for a chi-squared test for homogeneity is very similar to what we've already studied. The data comes from a random sample. We are going to check the 10% condition. If you wanted to, big N has got to be greater than or equal to 10 times little n, if you will. And all expected counts are at least 5. So they could be equal to, they just got to be at least 5. So again, the expected counts are found by taking row total times column total divided by table total. Oopsies there, pardon me. And the degrees of freedom are different. It's the row total minus 1 times column total minus 1. So just think about your time as a matrix, and it should help you here. So if you go back to your Algebra 2 skills, maybe when we talked about it, for the row total, column total, table total, but also right here with degrees of freedom. With 4 degrees of freedom. So just looking at this problem, talking about the types of music, we had our observed counts. So this was our starting block. Those were my observed counts. And then I wanted to find the expected counts. So if you look, the French entree with no music, it's 30 orders, and the expected count is 34.22. Again, if you wanted to see that, it is row total right here, row total 99 times the column total of 84, and you divide that by 243. That's how we're going to get the 34.22. So we did that for each table. Good news is you could get all these expected counts in your calculator. So there is a process for doing that. So your calculator can give you all the expected counts really fast, but you do need to know how to calculate these all on your own. So when we calculate the chi-squared statistic, again, it's still going to be 30 minus the 34.22 quantity squared divided by the 34.22. If you do that for all of your values here, we get a chi-squared statistic of 18.28. Earlier we stated a significance test that there is no difference in the true distributions of entrees ordered at this restaurant when no music and French accordion music or Italian string music is played. The alternative is that there is a difference in the true distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Our calculated test statistic is 18.28. So we could use our calculator to calculate this, but again, I need to find the degrees of freedom. So if we were to look at this, I had a 3 by 3 matrix. So 3 minus 1 times 3 minus 1 is 2 times 2, which is 4. So the degrees of freedom here is 4. So if I wanted to calculate a chi-squared statistic with 18.28, I used 1,000. We could use 1 times 10 to the 99th. 4 degrees of freedom, sorry about that. we got a p-value that is 0.011. So that's a pretty small p-value. So I'm going to skip down here to part C, and it says, what conclusion would I draw? Because the p-value of 0.0011 is less than our default alpha of 5%, we would reject the null. And we have convincing evidence of a difference in the distribution of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. So that would be the conclusion. Now, a follow-up would be, like on the AP exam, they may ask you to interpret the p-value from the calculator in context. And this is that phrase that I'm saying you guys need to remember. So that is assuming that there is no difference in the true distributions of entrees ordered in this restaurant when no music, French accordion music, or Italian string music is played. There is a 11/10,000th probability of observing a difference in the distributions of entrees ordered among the three treatment groups as large or larger than the ones in this study. We saw that way back in chapter 9, I believe, and that's our first interpretation of P. So if you need a review, please go back and take a look at that. So the chi-square test allows us to compare the distribution of a categorical variable for any number of populations or treatments. So we could take a look and see which one of these is the greatest contributor to our chi-squared value. Which one has the biggest difference? So if you look, these were right here that I'm highlighting in blue. Those were all my expected counts. And then everything here that I'm highlighting in red, that's the contributing factor to the chi-squared statistic. So when you take a look, there are really two cells that stand out, and that's the cell right here and this cell. Those guys greatly affect our chi-squared statistic. And you just see that over here that we are led to the conclusion of orders Italian entrees are strongly affected by Italian and French music. So that was our second row, and that was when the music was playing, what entrees were ordered, and those guys contribute the most to our chi-squared value. So they may ask you, again, that's a feature. Once you run our calculator, you'll see that in the calculator option. Okay, taking a look at our problem, it says, has modern technology changed the distribution of birthdays? With more babies being delivered by planned C-section, Miss McDonald's statistics class hypothesized that the day of the week distribution for births would be different for people born after 1993 compared to people born before 1980. The tables show the observed and expected counts for a birthday study. Does the data show convincing evidence that the days of the week distribution has changed? Okay, so we're taking a look at our tables. This is, in the past, would be presented to you in the AP exam. What you have here are all your observed counts. What we would need to do, if it was the AP exam, was we would need to show the expected counts. So you could just put expected in parentheses. So just to recall, remember that this is 21 minus 77 divided by 150. But you can't have a negative value, so we're going to change these to be positive. So that's why I'm going to do 77 right here, minus 12, 77, minus, 21, all over the table total of 150. So remember, that's how you would get that. So this gives me 10.78. And this again right here, 21, 73. So I'll do 73 minus 21, and I will divide that by 150. that would give me 10.22. I'm going to pause the video for a moment and just fill in all the expected counts. Okay, so I got all the expected counts in. That's going to help us later on in the problem. So the null hypothesis would be that there is no difference between the distribution of birthdays for each day of the week before 1980 and after 1993. The alternative is that there is a difference between the distribution of birthdays for each day of the week before 1980 and after 1993, and we're going to test at 5% significance. We are going to assume that there were a simple random sample of 150 people in the study. It is now safe for me to see that all of my expected counts are at least 5, and it is safe to assume there are more than 770 birthdays before 1980, and there are more than 730 birthdays after 1993. We are going to conduct a chi-squared test for homogeneity. So I'm going to calculate my chi-squared statistic. If this was the AP exam, it's okay. All you have to do is show how you would calculate it. So we did the observed minus expected, quantity squared divided by expected. You do that for all of those cells up there, and we get a chi-squared value of 6.5. To calculate the degrees of freedom, because it's a two-way table, I have 7 rows and I have 2 columns. So 7 minus 1 is 6, 2 minus 1 is 1, so the degrees of freedom is 6. Probability of chi-squared being greater than 6.5 is equal to the chi-squared CDF. Lower bound is 6.5, upper is 1 times 10 to the 99th. It's 6 degrees of freedom. Gives me a p-value of 0.365. So since p is greater than alpha, we will fail to reject the null. Mr. No forgot to write in here that 0.365 is definitely greater than 0.05. So now I have to conclude in context. So there is not convincing evidence that there is a difference between the distribution of birthdays for each day of the week before 1980 and after 1993. All right. At this time, I'd like for you guys to try this problem on your own. And I would like for you guys to submit this to me. It's going to be a full write-up for the chi-square test for homogeneity. Please make sure you're watching the videos, and this is going to be a way for me to check to make sure that you guys are indeed watching the videos. So you'll have an assignment tonight on top of the reading quiz, which is due Monday, but I need you guys to submit this to me before 8 a.m. tomorrow. I hope you guys are doing well, and I look forward to the Zoom chat today. Take care, man.